Okay.
Hey, yeah, welcome to Coffee Compiler Club. Here today to talk about all things to do with compilers and language runtimes and garbage collection and register allocation and anything and everything that comes around. I have special guest Ian Rogers going to talk about some cool stuff he's done recently. Um, and it will be, yes, register allocation and or garbage collection, but we'll open the floor to all kinds of other questions as we go to. And with that, Ian, take it away.
Okay. Thanks, Cliff. So I used to work with Cliff at Adult Systems many moons ago. I first came to the Bay Area to try and visit Cliff. He was out of town. I failed. so, um, and I wanted to kind of Cliff gave me the floor to talk about register allocation, but I thought I'd talk about a few other things first because I think they're cool and they're kind of under publicized. And so if I've got an opportunity, I'll talk about them, and they seem like a good opportunity. Um, so let's see. So I've got the next slide up. Okay, so the first one, and it's kind of like it's going to be like how the talk is I came up with this thing that I called the Beyonce principle. So I'm working on Android, and I'm doing a new runtime. So this is the art runtime that everybody uses on Android these days. Um, and managers being managers, they want to manage risk. And if you change the runtime, hey, that's a big load, of risk. So we weren't sure we were ever going to launch the new runtime because of the managers. And one particular problem we had was that people expected everything to be, the way it's always been. Um, and so I kept saying, well, if you care about it, put a test on it. And in my silly little way, I was like, okay, that sounds a lot like the Beyonce song. So if you want it, put a ring on it. Is Beyonce's way of saying it. So I made this as a little joke within my team, and since then it took on a life of its own. And it's shown up in Titus Winter's book as the Google Beyonce rule, and so on. And it was just me saying something silly within my team to amuse myself. And as my mother would say, little things please little minds. So that's me in a nutshell, a little mind. So the tone of the talk, I wanted to talk about nerdy things that kind of appeal to me and that are difficult to find. I would have appreciated somebody sharing these things with me. I gave a Java user group talk on JVM internals when I was at Azul, and YouTube comments are brilliant. If you're feeling, full of yourself, go and read YouTube comments, and it'll, bring you back down to earth quite nicely. So eJohnsify, who isn't a sibling of mine, but clearly knows them, their comment was, he seems a bit smug, as if he's so remarkably impressed with his own intelligence. If he'd lose the smugness, it would be much easier to watch. So I apologize in advance for my smugness and all of my many other failings and so on. Be gentle and kind with me. Go and vote up eJohnsify's YouTube comments and tell them how awesome they are for saying that. I'm talking in a personal capacity, and I'm not reflecting the views of my employer in any way. Okay. So the first thing that I did, and this is back at Azul, that I thought was cool, was read barriers without an extra read. So I'm going to kind of explain that. So I about 15 years ago. It's probably more like 20 years ago or 25 years ago.
That is Zool.
Um, no, like the opinion that you couldn't do concurrent collectors. Like these days, ZGC is the norm, and Shenandoah and so on. But kind of before pre-Azul and when Azul were doing Vega, there was very much an opinion that you couldn't do concurrent collectors. You needed to have some stop the world in there, and so on. And when they did the second version of the Jones book, the GC handbook, um, they put the kind of like the concurrent and pausing collectors, and then they went, oh, but there's these real time collectors. So the chapter after is like the real-time collectors, as if they're somehow better than the pause-free ones. And the thing to remember about real-time collectors is that they're not high performance. In fact, they're absolutely terrible performance. And if you want to do real-time, you should switch your caches off, and then your performance will be even worse. But yeah, you're real-time. Jan Vitek has a really cool talk comparing real-time garbage collectors to non-real-time garbage collectors, and finding that the non-real-time garbage collectors are doing a better job of being real-time than the real-time garbage collectors. And Jan's awesome. Yeah. Okay, so I'm working with Cliff. I'm at Azul Systems, and we're going to do a new product which is going to use commodity x86. So concurrent garbage collection, people try to make garbage collection sound like it's magic, and it's not. Concurrent garbage collection is only hard because objects can be in two places. And I'm going to call the two places the from place and the to place. So we've got the from space and the to space. So if I'm compacting things, I want to move everything into the to space. If I'm moving things out of a nursery, I'm putting them all into a to space. So if things can be in two places, then I have a problem in how do I compare references, and how do I load and store through those references. So we have these from and to locations, and you can try and have pointers to the from location and to the to location. The metronome garbage collector that IBM did this to some extent. Early versions of Shenandoah did this to some extent. But in general, you want a two-space invariant, which is whenever you have a reference lying around in a register, you know that it's pointing to the to space. So we've got lots of different approaches for doing read barriers. There's the Brooks approach, where you have a pointer at something, it's an object, and in that object is a pointer to itself. And whenever you get that pointer to an object, you have to load through that pointer that an object has to itself. And then when you're moving an object, you change that pointer to point to the to space, so that then you'll get forwarded along to the to space. With Baker, you have a reference that you want to load, and for this one, the object itself has some metadata saying, can I trust this reference to be a to space pointer? And if it's not, you set some metadata in the object header. And so when you load the reference, you have to load the metadata, you do a metadata check, and if the metadata is bad, then you go and do extra work, and you go and turn your from space pointer into a to space pointer. For the Azul Vega, there was an LVB instruction, and the LVB instruction would...
you want me to do this one?
you could. Well, you've loaded a reference. You want to check that reference is to a to space, and the LVB instruction is the thing that enforces that. Behind the scenes, there's a bitmap and a lightweight trap, and so on.
The thing that you're missing is it cycled. You have your read barriers all do two loads. This one's half of a load. It cycles the TLB on the loaded value. So it doesn't actually do a full load on the loaded value, but it does cycle the TLB.
So what does it cycle the TLB mean?
It pushes it through the translation, which then fails if you're in the wrong space. That's where those extra bits are stored.
Right.
On the Zoom, are my slides showing up for you? Because they're not really showing up for me.
They are for me.
Okay, that's good. That's all that matters, and that's what will get recorded. So, I mentioned compressor at the end because compressor was kind of like of academic interest, but it's now what they're using in art. And with compressor, rather than having metadata on an object, you just protect the whole page where these gray objects are, and then you'll get a fault when you try and access them. And then you go and blacken all of the references within the objects, which sounds hugely expensive to me, but it's not my problem. I suspect.
You have to blacken the references on the whole page?
Yep. If you want to unprotect it, I mean, you could shortcut it.
Okay.
Yeah, so I suspect it's just being used for background compaction, and then you're non-moving most of the time, or you're doing stop the world pauses. But yeah. So we've got lots of read barriers. I'm going to Java 1 in 2010, and I'd asked us. I'd been good when I left Manchester. I gave back all of my equipment because I thought that was a nice, the proper thing to do. And I'd been given this laptop from Azure, which was quite big. And I was going to Java 1, which was at the Moscone Center in 2010. And I was worried about being mugged or breaking the laptop. And so I trusted myself to carry a notebook and a pencil. And I was thinking about read barriers. And I came up with some, captured some of the thoughts that I'd had about when you could avoid read barriers and so on. So if you're searching for something in a list, you know that if you find it, it must have been a 2-space pointer, so you didn't need to read barrier it. So there's a bunch of those ideas which are written down in this reducing and eliding read barriers paper that I did. But then I really on the train, and what I was thinking about was just chaining through a linked list. And if you imagine that with a Brooks read barrier, if you have 4 elements in a linked list, you're going to do twice as many loads, and they're all dependent loads. So you're going to end up with 8 loads as you iterate through the linked list, and it's awful. I think I scored 1,000 nerd points because I came up with a production use for XOR, and XOR everywhere. And so I was definitely patting myself on the back for that one. And so the idea is that the thing that you're loading from has to be in the 2-space. That's the 2-space invariant. And what you're trying to do is check whether the thing you're loading is also in a 2-space. So if they happen to be in the same region of the heap, which you can test with an XOR and a test, then you know that they both must be in the 2-space. And so this is how you can do a read barrier without any registers and without any load instructions. I figured this out on the train going to the Moscone Center, and then had to wait until I could go home in the evening and go and code it up. And I had a working thing the next day. It wasn't quite working as well as I hoped. Michael Wolff came up with a better approach, which was a notion of GC state, which he used in the high bits of the reference. And that's the approach which is pretty much used everywhere in Shenandoah and ZGC and C4 and so on. But it all came from me not wanting to carry a laptop to the Moscone Center and only having a pencil and some paper. Okay, so transactional memory was a thing. It's no longer a thing. I think.
Well, wait a second. Back up. Does anyone else want to ask any questions about what was going on with read barriers? Just like change topics here.
Boom.
So like
I need to get some what was going on with read barriers? Should I sound more enthusiastic?
Yeah. I'll see if somebody has a more specific question. Is going to throw out comments on this. The jump to having a 2-space invariant opened up the sort of the world for concurrent GCs. They like prior to having the 2-space invariant, there was a lot of grief in many academic papers about bad ways to solve the problem. And when you switch to a 2-space invariant, you had to have a read barrier, and reads are 5 times as more common than stores. So everyone thought this is too expensive. But processors kept getting faster and memory did not get faster. So when you went from 2 loads back to 1 and you threw some dirt cheap integer ops in, suddenly you could have a read barrier. And that made a big difference in what kinds of GCs were possible.
Well, I also think 64-bit pointers were a big change, and And the fact that you had enough space in a 64-bit pointer to start squirreling away things like GC state, then, you know, I think that, you know, it wasn't that Brooks and Baker and so on were naive. It's just they were working on 32-bit systems and they didn't have all of this space in their pointers to start squirreling away metadata. So
yeah.
I mean, the other thing is the gulf between CPU performance and memory performance just kept on getting wider. So you could hide a lot of processing between cache misses. And so, you know, the XOR, the if, you know, all things that we used to think were not, XOR is never expensive, but a conditional jump used to be expensive.
Yeah.
But compared to a memory access, it's nothing.
Nothing.
Like zero, literally. Like, yeah.
Well,
especially if it's covered by branch prediction. So
I work on performance counters these days, and I'm impressed. You know, Intel are routinely retiring 2 branch instructions a cycle, and that's just
really 2 a cycle.
Really,
2 a cycle. 1 a cycle, that seems fair enough, but 2 a cycle, you know, and it's like going beyond that. Anyway,
is that 2 a cycle per a single thread?
Thread as in hyperthread.
Yeah.
So yeah.
Did you want to add something, Kirk?
not anymore.
Okay, fine.
I want to hear the rest of this.
All right, move on.
Two of these in a cycle.
So like before I came to Azul, I was actually working in a university on transactional memory, and there was all of this, you know, enthusiasm for transactional memory solving all the world's problems. And I think we might get back there, but just slowly and with baby steps. You know, have you come across memory rename stuff, where like Intel are promoting memory addresses into registers and things like that, and that's a very speculative thing to do and feels very transactional in its nature. Yeah, so transactional memory. It was a big research thing. I worked on it. Then Brian Karlstrom, who's on the Art Runtime, he'd also worked on it, and we were trying to think about how to do an image for the Art Runtime. So we wanted a pre-cooked image that we could throw into memory on your phone, so that we didn't have to do all of the JVM warm up and loading this class and the other. And also, when we generated compiled code, we didn't need to worry about all the slow paths. So, you know, the interpreter specs for Java are fairly egregious, and they require you to go and resolve symbols and this, that, and the other. And we didn't want to be doing that. And so the problem was like, well, how can we do things like run the class initializer for integer? And the class initializer for integer, all it does is create 256 boxed integers. And so on. So we wanted to have integer be initialized. So we needed to run the class initializer and snapshot the heap. That bit's all pretty easy. We've done it before in JIXRVM. The problem was, well, we just want to do this for a big long list of classes. What happens when something goes wrong? Like they do something like try and squirrel away a file descriptor or some native resource which isn't going to be there in the booted runtime. So Art has a software transactional memory in its interpreter, so that it can run these class initializers. And if they do a non-trusted JNI call or something which hasn't been special cased, then it aborts the transaction and rolls back all of the heap changes for that. It's not a particularly high performance software transactional memory, but it is a software transactional memory. And so transactional memory has escaped academia and the Vega processor a little bit more than would be obvious.
Yeah.
So
go back.
Go back.
Yeah. So you're saying that the Art runtime, but you're talking about the ahead of time compiler piece is trying to, ahead of execution, trying to run all the class initializers, and as long as they don't do anything screwy, you get away with it. And if they do something screwy, you back up, and then I guess at runtime you just run it now in the interpreter.
Yep, you just run it again. It doesn't. You could have compiled it with all the slow paths in there, but yeah, it's the main thing is to try and get rid of slow paths and to have this like pre-cooked thing. And we had, telemetry on the when you aborted a transaction. So you could go and look at when that was happening. And then you could go and say, oh, well, if we tweaked the behavior of this, or if we moved this file descriptor into an inner class that was hidden away from everybody, then we can initialize most of the things. And then we can just do this piece later. And this was with a view of having everything pre-cooked. In the regular kind of Java community, they've been doing something similar. There's class data sharing and so on, but they've been trying to go like, oh, how do we work? We want things to go into the image. How can we do it all and so on? And it's like annotations are the solution to everything. But really, I was quite pleased with the software transactional memory. It meant that the programmer didn't need to know anything. We would just magically do it all for them. But they could get a slow path behavior, in which case they would need to kind of look at the logs and go and figure that out.
Well, if you took the slow path, things would just work.
So the slow path could be, go and resolve this symbol, or go and work out the offset of this field in this class, and all of the usual interpreted semantics in Java that you have before you quicken the bytecode and so on. But
I'm saying in general, the program would run, as opposed to on my phone, the program would abort and tell the programmer back at Google to go fix it.
Yeah, everything would run.
Okay.
And the fact that Android runs an application called the Zygote, which is just sitting there listening on a socket, waiting for people to say, "Hey, go and run this Java application, run this," and then as soon as it gets that message, it forks. It has a pre-warmed one, but then it forks one to then be the next waiter for something telling it to go and forks to run something else. So we knew what the first application that we were going to run was, which was the Zygote. For the actual applications themselves, it's tricky to run the class initializers without violating the interpreter semantics.
Right.
But you can do it for things like the reflective methods and things like that. So bits of metadata associated with things, because those are the things that you control. So those tricks are played in art today, but yeah, the ahead of time initialization is limited. The thing which is nice is using the software transactional memory to make this an easy thing to develop with.
So this is all about faster startup time on your Android, which is fine. It's just interesting. And then Kirk reports that the read barriers paper you put a link to is locked. You might want to, after the talk, go sort that out.
Is it?
Well, locked for somebody. I haven't tried it myself.
It says it's locked and it says get access. So we can read the abstract.
It's an ACM thing.
Oh yeah, you have an ACM account. Okay. Would you please figure that out afterwards? Maybe a PDF. I don't know what your rules are on that paper. Let's sort it out afterwards.
Yeah. Yeah. Anyway. Okay, I'll try and sort it out. So the next kind of like very small thing, which isn't a full thing, was so there's a certain set of people in Google who like to espouse fluent programming, and I always think that these people should have it on their tombstone, that their tombstone is written in a fluent style because it's so fluent to them. So I've given an example of what my tombstone would have written on it. So here lies Ian Rogers, he's unbearably smug, but in a fluent style. But anyway, so people are writing all this fluent stuff, and the problem is that you get a null pointer exception somewhere on this line. And the question is well, where did I get this null pointer exception? Because I need to know that to go and fix it. And so I had a saying in Android, which is exceptions are exceptional. We should never spend any energy trying to make exception throwing fast. Spec JVM 98, Jack is not a production workload. Yeah, it is stupid. there are things like the Capo benchmark does this like Russian nesting dolls trick with class loaders, and class loaders like to communicate information with class not found exceptions. But in general, just don't care about exceptions. And in this case, I added to the null pointer exceptions, hey, I'm trying to call virtual method this or something like that. The Android developers were really, really happy about this. Kind of like disproportionate to the amount of work that I put in. There was more work put into updating test expectations than actually implementing it in the VM.
It's amazing when you tell people what went wrong, how thankful they are for those little things. Like, really.
So I'll have to throw in here that back in that era where this was coming through C2, I had any number of people yelling at me that it had to be faster, that we were in direct competition with C and C++, and speed. And a minor amount of speed gain was to throw away the debug info that let you build a stack trace. Right? This was like, okay, I can shortcut NPEs or not. And there was a back and forth. And at some point, somebody said, you know, hot loop, whatever, blah, 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 go faster. And I threw out the debug info for building a reasonable stack trace for NPEs.
Yeah, and a stack trace used to be 10 methods deep. Now it's, you know, I've seen them into thousands. So.
The debug info that you throw out there is actually small. It saves some registers and some stores to the stack where you spill off things for just the set of methods you've inlined up to. So it's never very much, but it got a lot cheaper in the last 20 years. Like an x86 can sync any count of stores of junk things that'll never get loaded for like basically no cost.
But rendering stack traces sometimes takes, you know, a double-digit percentage of an enterprise workload.
If you go to
CPU.
the exceptions or exceptional model, which I totally am with, then you don't care. Hey, you're communicating with exceptions? Well, tough shit, dude. You shot yourself in the foot. I hope you enjoy it.
So yeah, so we did this in Android, and then about 5 years later, people started going like, it really sucks to be in hotspot because we don't get these error messages, and then it's now in hotspot. My thing about like Java workloads at Google is like, this is on the server side. People will do things like, oh, we'll just hold on to a few exceptions because maybe, you know, we've had some network problem, maybe something like that. If we start seeing a lot of them, we want to kind of start logging all of that stuff. And of course, the first thing that they do is they string builder to string it all.
Yeah.
And the fact that, you know, every like logging API takes a string and it doesn't take char sequence, the interface of string, means that what normally happens when they start getting all of these exceptions and they then go to render it is they get an out of memory error. So we went from having a networking issue to then servers falling over from lack of memory. And
you're trying to trigger me here, right? So
sorry?
You're trying to trigger me here, talking about these wonderful APIs.
Not everything's about you, Kirk. We're not necessarily trying to trigger you.
You're trying to trigger me. See?
Well, I'm still disappointed that you know, people keep inventing new programming languages and they keep making the string implementation something which is like not an interface, and it's frustrating.
Well, we've been told for so many years, over and over and over and repeatedly again, that, you know, garbage collecting dead data is free, so go ahead and allocate, because allocations are absolutely...
That's the trick. Allocations are not free. The garbage collection might be, but the allocation is definitely not.
Yeah. So I'm looking at an application here right now. I have a chart up, and this thing is allocating at rates of average Java object sizes at 8 gigabytes per second, which is amazing that the JVM can actually allocate at that rate. That's a really nice high rate. It's, you know, kudos for them to be able to achieve that rate on the hardware they're running on. You know, but however, if we, you know, Anyways.
All right,
Continue.
Ian, carry on.
Yeah, carry on.
Well, another example on the API side of it with strings is substring. The change from substring being a constant time operation to being something which would copy n things. And it seemed like an innocuous API change. It had big ramifications. If everything had been an interface and you got a substring, which was just, so it would have all played out. And yeah.
Substring is a different issue. The fight was, I held on to a 2 GB XML string because somebody substringed a tiny piece of it, versus every substring on the planet now allocates and copies. Both of these answers are kind of suck in their different ways, right?
Yeah, but you're in a managed runtime, so there are better answers.
I'm not saying that. I'm just saying, given an API that started out with substring, the answers are copy like shit, hang on to giant ass thing. Both of those answers were kind of bad. Yes,
and I think Java is finally fixing some of the problems because they've got a project now that is deferring some of the string rendering for logging and stuff like that. I forget how they do it, but I mean it's overdue and it's a good idea.
Yes. All right, carry on. Go. Move. Next slide. We're too long here.
Okay. So a concurrent non-moving generational garbage collector, and I'm going to try and do it in 5 minutes, which is ambitious, Cliff tells me.
Yes.
There are a thing called sticky garbage collectors, and it's excusable to not know about them because the first 2 editions of Jones's GC handbook don't cover sticky garbage collectors at all. But it was a trick done in the Bohm's Dieter paper, and they mention it in like a single paragraph. So maybe I can do it in 5 minutes. But the trick is that you hold on to the bitmap at the end of the last GC cycle, which tells you what was live at the end of the last GC cycle, and then you've got this new live bitmap. And the difference between the 2 bitmaps tells you what your new objects are. And when you come to mark, you only need to mark the new objects because you don't want to mark the old gen. So you don't do the transitive closure, the old gen stuff, unless your write barrier is telling you to do that. Okay. Oh, I've got some notes. Okay. So in this little diagram, we've got things which are in the old bitmap and the live bitmap. So it won't be freed because it was marked, and it was old it must be old because it was live at the last GC. And then the new ones have only got the live bitmap set and not in the old bitmap. So this is a way of doing non-moving generational garbage collection quite succinctly without having a nursery. So with write barriers, you've got a generational write barrier, which is going to tell you about regions of the heap that were, or particular addresses in the heap, where you can have an old to new pointer. And the reason you need this is so that you can treat all of these cards and so on as roots into the new generation to tell you what young objects are live. Another write barrier we have is a concurrent write barrier. And the purpose of the concurrent write barrier is you start doing your concurrent garbage collection. Whilst you're doing that, you could be loading, pointers and moving them around and so on, and that will hide the fact that these pointers are in use from the garbage collector, which is traversing the heap. And so the concurrent write barrier just says, hey, there's something in this region where something could be being hidden, and you can do both of them by just doing stores of a byte to somewhere in memory. So I've got a little depiction of a card table. The zeros show that nothing's been set in the card table. The FF is, hey, we changed something in this region of the heap. If it's a generational one, it's saying, hey, this is an old generation and maybe there's a new gen pointer in here. If it was a concurrent one, it's like something changed in this space since the garbage collection started. So the idea with concurrent sticky is we have this problem that we want to concurrently scan the new gen, but we've got the same card mark for both things. So we need to be able to distinguish the concurrent write barriers from the generational write barriers. So the first thing that the garbage collector does is it iterates over the card table and ages all of the cards. So it's going to make this FF value down to FE. We know any non-zero card is a potential root from the old gen. We know any card which is FF must be something which has been concurrently updated. So in the CMS, pause, we can go and look just for the FF cards. We don't have to go and scan every card again. So you can use Relaxed Atomics for this and so on. And because you can do multiple agings, you can support multiple generations with this approach. But basically, I think this has a lot of virtues. It's non-moving. There's no read barriers. It's generational. It's concurrent. What more do you want?
Compaction. You want compaction.
Sorry?
What more do you want? You want compaction.
So Jones was retiring, and like they were asking people for questions. So my question was, are moving garbage collectors overhyped? Okay, because it's like people always go, oh, you need compaction. It's like, well, why do I need compaction? It's like fragmentation. It's like, okay, well, C++ servers don't die all of the time because of fragmentation. Why must I have it for Java and so on?
Yeah,
and what they can do is they can point to somebody who says, well, he told me I needed it. And so I have yet to find anybody who can conclusively say that we need compaction because of this. I agree, compaction's nice. We can lower memory usage and things like that. But we have C++ servers and they don't die all the time.
Okay, so hang on. So I know Cameron wants to say something, but I'm going to throw in here. My data on this is old, but at some point in my late grad school, early hotspot days, somebody came around and said, compaction saves 5% execution time because of better cache locality. Because the standard young gen def pattern sequences, you allocate a bunch of stuff, it's 90% dead, the generational assumption works, you collect it. What you didn't collect because it's still alive is now allocated in order of time that it got allocated, and compaction generally brings them together, and generally, on average, they're related. There was a bunch of extra junk in the middle that died right away, but the things that stuck around were actually calculated, computed in order, and then they typically get used in order or near each other, and you get better cache locality. Now, that information is, like I said, it's dated. So I would love to see a more modern treatment on this.
Okay.
So there's things like Objective-C and Swift, which have got non-moving things in Python, and there's lots of counterexamples. I think there are lots of interesting things that go on with hardware prefetchers, and the recent M1 security issues around their prefetcher have kind of like, what they were trying to do was you were fetching a cache line, and they were trying to look through the cache line for things which looked like pointers so that they could start prefetching them. So that's really crazy. One of the things, if you imagine that you've got a reference counter in the header of an object, then incrementing an immutable object as reference count means that you end up owning that cache line, and that doesn't scale. So how can we increment reference counts without owning cache lines is a real issue. And there's a lot of good things going on in this space. And so I think there are good things. But the whole idea that we're somehow helping the prefetcher and so on and so on. What happens a lot in data centers is they have all of these fancy prefetchers, and we end up switching them all off, because they hurt us in the 3 nines and so on. And I have specific examples of that which I can't talk about. But yeah.
Right. So it sounds to me like there's still there's a common wisdom, and there's a long-term lack of evidence in either direction at this point.
Right.
Okay. Could I ask a question?
Yeah.
So did I understand if you're turning off prefetching in order to accommodate the GC and make it faster?
It depends. There are many different workloads. There are things around. So most L3 caches these days are victim caches, and so there's a lot of policy decisions which go on around L3 victim caches, and so basically you have a bunch of switches you can flip one way or another, and you have benchmarks you can run. So you flip the switches one way or another and see what happens. And especially if you're looking for like 5 nines, throughput and things like that, then you find that fancy feature X, which should be super awesome, usually hurts you somewhere. And I think Apple have been fairly badly burned with the cache prefetching, the hardware prefetching for the cache, with it being a security issue. But that's why we can't have nice things in hardware.
So that's a separate
That's
issue.
a separate problem.
Like my experience with the fancy flags when you're pushing the limits of things is that you're just robbing Peter to pay Paul. Nothing got gained on average. Instead, a little more here meant a little less there, and you get the non-obvious. It never, it's not faster actually.
Yep.
Cameron,
it's not my job to worry about it. So there are a bunch of things you can do to make garbage collectors fast.
Hang on, before you take off again. Cameron, did you have something you wanted to comment?
Oh, I had a different comment earlier, but long past its prime. What I was going to say is there are a couple reasons why compaction can be useful, but I mean, you really do have to look at the statistics to prove it. One of the things has to do with graph locality, but it takes a lot more intelligence than your typical compacting collector. And, and it's also a nice combination when you have a collector that has the ability to both in place, because most garbage collection won't move anything. And then, based on the statistics, can occasionally do a compaction. So you kind of get the best of both worlds, but it does have a complexity cost.
Yeah. I can believe that there are some cases like that, but it sounds more like a batch case and not something that's when you're serving stuff in a data center.
There's one other optimization that does work well with compaction, which is the non-fenced collection of immutable data. So you basically have two copies while you're collecting. So you're compacting without stopping anything, but it only works for immutables.
Right.
Yep. Okay. Anyway, there's some stuff about GC. Some stuff about why it didn't really stick. I'm a believer that basically the thing that everybody's working on, the people have reasons that they want to make something better. It could be promotion, it could be lots of other kind of like human factors and so on. And so the thing which ships and is switched on isn't necessarily the best algorithm and everything else like that, but it's probably the one which had most invested in it. It's true that you can't polish a turd, but you can hide a turd by making everything else, by making other parts of the runtime run faster and so on. So an example of this with IMIX was they could never get the IMIX collector into Jike's RVM, and what they did was they bumped up all of the inlining thresholds so that they inlined even more of everything. And then finally, they got IMIX to outperform generational mark sweep, and that should surprise garbage collection people because everybody thinks that IMIX is the bee's knees. Okay, register allocation. We've got 10 minutes left.
There's no timing here. There's not an hour.
Oh, okay. I'll run long then.
I guess it's a 2-hour timer with lots of room for Q&A.
What? I'm used to my kids' Zoom meetings, and it's like if they don't get stuff done in that hour, it's like they're zipped off, and then I'm like panicking. So we've got register allocation. People should be familiar with graph coloring and linear scan. It's a compiler coffee club. Come on.
Yeah, we're familiar. Yeah.
Tree scan is more obscure. So tree scan is, compared to graph coloring and linear scan, it's a new garbage collector. And it was built on top of like an SSA liveness model where they don't compute liveness by computing a fixed point. They do it through complicated properties of SSA, so on and so on. And the fact that they need like a very large paper to try and explain it makes me not very, whereas the regular liveness algorithm fits on a page. I'm kind of intimidated by it. But the point of this slide is to say, with graph coloring, you have to produce a graph. The graph is telling you you've got two things. You have edges when two things are live at the same time. Linear scan has intervals. If intervals overlap with each other, then that means things are live at the same time. With tree scan, what they do is they don't do any kind of intervals or graph. They allocate going forward. But the problem they have is if they have something like a loopback edge and a phi, they can find that they've put something in a register that they didn't want to have in that register. And what they have to do then is put a move on the edge going backwards. So they basically do suboptimal register allocation. They can't handle anything being in a register in the future. They have no knowledge of it. So it's a fast register allocator because there's no graph, there's no intervals, but it's a suboptimal register allocator.
I want to pile in here for a second. In C2, the register allocator is typically 40% of total compile time, and probably half of that time is liveness. Like there's a significant fraction of total compile time dedicated to computing liveness. So I'll agree with this slide. It's expensive.
In the original linear scan paper, there's like half the paper saying this is what linear scan is, and then another half of the paper going like, we think we can optimize it and get the interval creation down to being something reasonable if we hack around it in this way. There's early graph coloring work, but it's on like floppy disks where they're saying, the graph won't fit onto a floppy disk, and things like this. It's been long known that the problem is that these representations are expensive. How difficult it was for me to try and, I never got this paper that I'm talking about published. And I got so many idiotic reviewer comments back on it. I was just like, well, screw it. I'm putting it on archive.
I tried to publish my how to do graph coloring faster a couple times. And also both times the reviewers completely missed the point of the paper and went off on wild tangents that had nothing to do with nothing. And in the end, we're like, compare linear scan to graph coloring. And I'm like, dude, this is how to make graph coloring go faster. It's not trying to compare against linear scan. And they were like, no, can't do it.
Yeah, they were like, well, they in the end they were going like, oh, can you write this up as a poster or something? It's just like, come on.
Right.
If you're working in this field, this really matters to you, and you want to know what everybody else's tricks are. One of the things, the SSA book, so the SSA book is a new thing. The SSA book doesn't cover how to compute liveness on SSA form. They just go like, oh, just do it. And it's like, well, what's different about liveness on SSA form? Well, phi instructions have got multiple inputs, and those inputs aren't live on all of the back edges, and you have to do something special. Liveness on SSA form, and so one of the things that's in my paper is how to compute liveness on SSA form, because it's not written down anywhere else. And people just don't know. When you practice in it, then you know. But anyway, so when you're doing register allocation, there's lots of like silly heuristics that come up. The first one I've got is that if you move a register to the same register, then that's free. And so register allocators want to apply this heuristic a lot because zero cost is good. In the C1 linear scan register allocator, they have this notion of hints. So when you free a register, they want to reallocate to the same register. And the reason for that is it gives you more often than not two address encodings on x86. So they squirrel away this hint value. Something that Cliff and I did for the client compiler for Azul was if you're allocating 32-bit or less instructions, then we would allocate them from low registers to high. And if you were doing 64-bit operations, we'd allocate them from high registers down to low, because in x86, if you're going to do a 64-bit operation, you already have to pay for the rex prefix. So you can save some bytes by avoiding these rex prefixes. If you in a better register allocator like the C2 graph coloring register allocator, they treated all registers as equal, and it was very difficult to kind of like repeat this kind of heuristic thing that in C1 was just this dumb, go in this direction, and so when you're writing register allocators, a lot of what you're trying to do is dumb little heuristics, dumb little observations that you can do, which will save an instruction here and save an instruction there. One of the ones for the runtime I was working on was it was difficult to materialize constant values. You had to pay an instruction for it, and you lost a register. But it could be that somebody had just left that constant lying around in a register anyway. So you kind of want to conflate the two uses of the constant together. So there's a little heuristic that you could notice within a basic block to avoid an instruction again. So intervals and graphs aren't hackable. So a typical register allocator problem is I put this thing in a register, and now a divide or a multiply instruction wants that register, and it can only be encoded in that register. And so I've got to go and split the live range. Splitting the live ranges in the instructions is just like copying the value somewhere else, so it's not sitting in RDX, RAX on Intel. And adding that copy move instruction is easy, in the IR. But imagine updating the graph or the intervals to deal with that, because now you've got this new thing that exists. It didn't exist before. You know something about it because you've got the previous interval. How do you go and update the graph and the intervals for this? And the easiest approach is just to throw away your graph and intervals and just to recompute them all. But they were already hugely expensive to compute in the first place, and so on. So there are very, cunning liveness updating things, and they're tricky to implement and bug prone and things like that. And I think a key insight from the Sea of Nodes work is that every time you have some kind of side IR, they're a pain in the ass as a compiler developer. And intervals and graphs are side IRs. So the community should be working on register allocators that get rid of them. And TreeScan, existed before I did this work, and they'd got rid of it. I did this work ignorant of TreeScan. So the key property that we have when we're trying to do register allocation is we want to work out, can I put this instruction in this register? And the question we're trying to ask is, well, I can put it in that register as long as nothing else that's going in that register is live at the same time as this value. So the graph, the intervals, none of that mattered. The thing that mattered was this live at the same time property. And I can put something into a register if it's not live at the same time as anything else that's going into that register. There's exotic ways of computing liveness. I've never seen computing liveness using fixed points actually take a very long time to complete.
It was building the graph. It wasn't computing liveness. Yeah.
Sorry?
Yeah, it was building the graph, not computing liveness. I had to compute liveness, the classic bit vectory thing. It's fine.
Yeah.
Building the graph was expensive.
The maximum. I think trying to come up with a pathological case, I got computing the liveness fixed point up to like 6 iterations, but it was like I was actively having to come up with crazy ways to do that. It just computing liveness is not something I've ever seen take a long time, and so I'm kind of poo-pooing the exotic ways. The exotic ways are interesting because they're lower cost, but they're less hackable. And I give an example at the end here about we've got a basic block with these two values v0 and v1 in them. They're being assigned two constants. Both v0 and v1 are live out of the basic block. And so if I want to know, can V0 and V1 be live at the same time? Well, I can just go and look at the live outs of that basic block, and I can go, yes, here they are both being live out of the basic block. They're live at the same time. And I did that without computing intervals. I did that without having a graph. So that's the kind of
that's an approximation,
intuition.
right? I mean, that's a conservative approximation. It's always correct, but they could both appear in a single basic block and be forced live at the same time, and you would have missed that one. This is an easy case. You know that they're live at the same time. But I could have...
Right.
Okay.
So the paper goes through kind of like every single possible case, between blocks, in the same block, everything else like that.
Okay.
And I've spared you going through that in painful detail because it was painful to implement and so on, but it's not that bad. And if you do need to re-implement it, go and look at the paper and copy what I did. It was in production use.
Okay.
Okay, so I said that. So this Cliff asked me to colorize the graph. I couldn't find the original source. I drew boxes over the top, so that's why it looks a bit skew-iffy. So what this is saying is the green boxes on the left are saying for this top graph is the green blocks is the number of instructions which have got 0 uses. So if you've got a function call or something like this, nobody's using the return value. Sorry?
Conditional branch. A branch.
Conditional branch, a store.
Are you doing flags? Is this register?
In this one, it's a byte code to register like byte code thing, so no flags. It's very one-to-one. So a third of instructions have just got no uses. So why do we need an interval with them? 60% of instructions are defined and have their only use in the same block. So you create a value, a constant, and the only use of that constant is in the same basic block. And then we've got greater than 1 use. So there's kind of like this final 10% where there's like 5% where it's used more than once, and there's 5% where it's used in more than one block. The bottom graph is showing, that's just showing that most things have 0 use. The majority of things have got exactly 1 use, and then there's kind of 10% where we've got more than 1 use. The breakdown above is are the uses coming from the same block or different blocks? If it has 0 uses, then that's captured differently. And then the summary of this is that these liveness models we have they're overly complex for the SSA common case. So for linear scan, you'd have an interval. The interval would be associated with an instruction. The interval would be saying, okay, I'm live in this region and I'm live in this region. So you've got a list of pairs of, a list of regions where regions are pairs of things. It's a lot of overhead. I've got an example coming up in the next slide. So this is a walkthrough of like how the algorithm works. But basically, when we do linear scan, normally you're trying to put an active interval into a register. And in the approach in the paper, what it does is it puts an instruction in there rather than an interval. If a instruction can have future uses, so when you allocate fee instructions, you have to deal with the fact that fee instructions are parallel moves. And so there's a common approach to do that with injecting what I've called fee moves, which are like just move instructions in the previous block, which ensure that all of the values going into the fee are in the same location. And so you kind of co-allocate all of the fee and the fee moves at the same time. So something like that, you have this fee instruction that you're allocating. You've got these moves which need to be in the same register. They're going to be active in that register at some point later in your traversal. And so you need to keep that information somewhere. And so we have this future active set. And so we can allocate a value into a register as long as all of the values that could be in that register aren't live at the same time. So we do that by checking what's active and what's in the future active.
We need the example.
Sorry?
We need the example.
Yeah. But the active check is just, is the value, is it null? And then the other thing is that you can free a register when you've come across the last use of that value. So it's useful to know last use, and I'll come back to that later. So here's an example. We've got 4 basic blocks. I've given the live ins and live outs, which I hold on to. The first basic block is the basic block I showed before. We've just got 2 values, v0 and v1, which are constant values 1 and 2. Going into the left-hand basic block, v0 is live, v1 isn't used there, and it's not used in the final basic block, so v1 isn't live there. We're going to assign this v2 to the value 3. And then below that, we've got this phi move where we're copying v2, and I've given it a new name. Live out, we've got v0 and v3 because v0 was live in. V3 is live out because it's going into the phi. So now going over to kind of like the right-hand side of the branch, we've got v0 and v1 are both live into this one. V1 is going to be copied into v4. It could be doing some operation and so on. I've simplified this so that it's an example that fits on a slide. We've got a phi move of v4 into v5. And then in the final basic block, we've got the phi that's combining, v3 or v5, depending on which edge we go down. That's giving us v6. And then we're going to add on to our original constant 1, the value of v6. Now, obviously, you would constant propagate this and everything else like that. It's a contrived example for making it easy to kind of walk through what the algorithm's doing. So the active is what's in the register at the point of the traversal. And the future active is what can be in the register at some later point of the traversal. So the first thing we're going to do is we're going to allocate v0. And we had 2 registers, R1 and R2 up here. And R1 was free, so we just assigned v0 into R1. And I've denoted that on the IR by putting like R1, v0 is in R1. You wouldn't really implement it this way in the compiler, but it's just to make it so you can see what's going on. Yeah. So the next thing that's going to happen is we're going to allocate v2. And on the table on the right, you can see that we've got v0 that's active. And now we have v1 that's active. We're going to process the left-hand branch first. That's why I kind of tried to emphasize the arrow a bit more. And what we do now is we compare the live outs with the live ins. And we see that, that they're not exactly the same. If v1 is used in the future, then that means we need to move it into the future active. Otherwise, we can free the register. So in this example, v1 is used in the future because it's used in the right-hand basic block. And so because of that, we're going to move it into the future active registers. So on entry to this block, we know that in the future, v1 is going to be active. So this is like a liveness hole in regular intervals. We know that v0 is active in R1. And so to now we come along and we need to allocate v2. So we put v2 into R2. The use in the phi move of v2 is the last use of v2. So we know from that we can free up the register. So the register's gone from the table. And now we need to allocate v3. And when we allocate a phi move, we allocate all of the phi moves in the phi instruction all at the same time. And so to be able to do that, when we allocate into a register, we need to check the live at the same time property for all of the fee move and the fee instruction when we do that. So we do this, and we find that R2 is available because it was just freed when we freed V2, and we allocate all of the values at the same time. So V5 has been allocated, V6 has been allocated. Because we were allocating V3, it goes into the active register, and V5 and V6 go into the future active set. Okay, so now we're going to process the right-hand side of the branch.
So hang on. So when you did the left-hand side, some future point, there could be arbitrarily large amounts of graph on the right-hand side till you come around to this fee again.
Yep.
And so you're just pre-allocating R2 to the fee without knowing what's on the right-hand side leading up to it.
So I'm allocating V3 into R2.
Yeah.
But I'm also at the same time allocating V4 and V6 because
V5 and V6.
Sorry, V5 and V6, yes.
Okay, but without knowing the context around the right-hand side.
Right.
Okay.
And I know that there's nothing live at the same time as any of those things. Otherwise, I couldn't put it into that register.
But you haven't. How did you know? You haven't asked the question. How did you know there was no? Oh, you have just saying arbitrarily have live at the same time available to me, which you're picking out from. Where did you get the test live at the same time that you ran on V5 on the right-hand side?
So the test is I'm allocating V3,
yeah.
But we decided we're going to allocate V5. So if I go back to here, we're allocating V3.
Yeah.
So I come along to R1. R1's got something active in it. Can I put something in there? No, there's something active in it. So move on to R2.
Right.
I'm at R2. I can put something in R2 as long as it's not live at the same time as anything that's either that's in the future active. So we have V1, which is in the future active. Okay. So I need to ask for V3, V5, and V6. Are you live at the same time as V1? And if they are live at the same time as V1, I can't allocate into V2.
Yeah, how do you ask that question? What is the test?
Okay, so the test is V3 live at the same time as V1? Okay, and I can look. So V1 isn't defined in the same basic block. It's not live in, it's not live out of the basic block. So it's pretty easy just using the liveness from the ins and outs to tell whether V1 is in there.
Okay, so it's not your future active set. So you're just saying I'm not live as V1, so I can grab it. You're making an allocation decision right now for V3, obviously, but also for V5 and V6.
Yes.
And you're right now claiming the only thing I have to dodge is V1.
Yep.
And everything else I'm going to dodge when I get there because they'll dodge me instead of me dodging them.
Yep.
Okay, fine.
That's exactly
I'm with you now.
Yeah. And I can
quick question.
Sorry. Yeah.
I'm just wondering, are you doing a liveness pass beforehand? Is that how you're getting the live in and live out stuff?
Yes.
He's doing liveness, but not an interference graph.
Okay, so liveness, but not interference graph. Okay, so that's all done in advance. So you've got. Okay, so second question. Your future active table has V1 while you're looking at this block on the left.
Yep.
But like, doesn't liveness already know that V1 in the context of looking at this graph is dead anyway, or it's not relevant?
That's what I thought as well.
It knows that V1 isn't active. So it knows that V1 isn't live in or live out, but we need to remember that it's going to be active at some point in the future. Okay,
He
because we
says,
haven't
Don't we
processed the
just
right-hand side
come
yet.
back to that and sort of is that maybe because when we go back and then go down the right hand side, we
you now have
don't
to
like
deal with
restore any state. We're just sort of
Yeah.
like everything that you need to go down the right hand side is already sort of present in what we're doing.
I have my take on Ian saying future active in the future. It really means active somewhere else in the graph, not time-wise future. Somewhere else in the graph. Future in his algorithm passing, somewhere else in the graph it's active.
I see.
If
right?
you put it, if it's anywhere else in the graph, you know, going backwards or forwards in time, then you end up building an interference graph, and then it's not really helping you save anything. The point of doing it during the traversal is you know, the future actives are in general very rarely used, and when they are being used, you generally have something sitting in the active as well. So I have numbers to back that up. But the point here, you know, when we're allocating V3, why are we still holding on to information about V1? It's because we haven't allocated V1 yet. Well, sorry, we have allocated V1, but it's still live somewhere where we haven't processed it yet.
We might yet conflict with we don't know if we're going to conflict with the choice of V1 and R2 yet.
Yep.
When we get to that right-hand side block, that's when we'll discover whether or not we have a conflict for V1. Since we don't know, and we may have a conflict, we'll just act like we have a conflict. We won't pick we won't pick it R2 there if we were to conflict with V1. So we go ask the question, can we be conflicting now with V1 because it's in our future active set? And he says, live at the same time with V1, is that possible? Well, it's not live in, it's not live out on the left-hand side, can't be conflicting right here. So no, it's not a conflict.
So if you did the analysis going down the right-hand side first.
Yeah, you would get a different set of things here.
This is like a different set of things, right? But it would work
finish this example and then repeat it going down the right-hand side first. I think that would be a useful thing.
Testing my brain. Okay.
So then you have V1, right? Going to register 1, and V0 is register 2 future active.
I would have to step it through to pull it out. I'm still staring at this example. But yes, something changes for sure.
Yeah, future active just seems like the wrong word for describing it.
Yeah, that's future active threw me off too, Ian. I'm thinking active elsewhere. Not yet seen in the algorithm, but definitely alive somewhere else.
Not yet is sort of implies future. You know,
I was trying to say it succinctly, so but if there's a better way to say it, I
think you have to describe future as in future of processing of this graph as opposed to future time-wise.
Yeah, it's
right?
nothing to do with
so this is a point in time, and you're looking at, I need some time to analyze this, so I might find something in the future analyzing it. But
normally when you do linear scan, you've linearized the graph, so it's all linear when you're working left to right. So
that's what I assumed.
Put that on the slide. Sorry.
That's what I assumed from the beginning, and maybe it was a bad assumption. Not in this case, but not everyone made that assumption.
Future with where the running program would run into, as opposed to the graph, the laid out where the algorithm would get to in a minute. That was my confusion. The word future was being done in the execution time as opposed to the algorithm time.
It's compiler time, right?
Yeah, or compiler time, yeah.
So
compiler
time future, not an algorithm time future.
Well, especially since the arrows are control flow in this case, you know, it's kind of confusing when you have the term future and you have control flow arrows. So that definitely.
You have a DAG, not a left to right. I mean, I assume you did something like reverse post order, sort the list, and you're just walking it left to right. But there's actually arrows there. Fine. Or yeah, carry on. Finish.
Yeah, but if you go down the right-hand side, that would be, then you might see it.
Okay, so I talked about this. We're going down the right-hand side. Okay, so the live outs we just had were V0 and V3 on the left-hand side, and the live ins here are V0 and V1, and so they differ. in this case, I've not written out the if then else. But what we're going to do is we're going to move v3 to future active because it's no longer active, but it will be active in the future. And I'm going to move v1 to active because it's live in. So the next, the thing that's changed between this slide and this slide is that v3 has jumped from to the future active and v1 has jumped to the active. Okay, now we've got the last use of v1 here, so we can free the register. So R2 is no longer in use, and now we need to allocate v4, and R2 is sitting there temptingly, but we've got to do the live at the same time tests, which would be against v3, v5, and v6. So we allocate v4 into R2. Now we've got the last use of v4, and so we can free that. We can free the register, and here we've got the fee move of v4 into v5. v5 was already allocated; it was in the future active, and so all we need to do in this case is just move v5 from future active into R2. If something were already in R2 when we were at this point, then it would let us know that things were broken, because you should never get to the case of like an instruction that's in future active. And when you get to that instruction, if it's in the future active, you should just be able to move it into the active. Otherwise, things are broken.
I would have expected that if you had that case, it means that you need to insert a move.
So if you need to insert a move, then you need to kind of like recompute the liveness, because you've got a new instruction, a new value at that point.
So if you had a conflict, are you asserting that you don't have a conflict, or you have a buggy algorithm, as opposed to?
Yeah, you've got a buggy algorithm. That's it, and it's not really worth saying more than that. So now we're going into the last basic block. If we union the live out of the left and the right block, then what's live out is the same as what's live in. So there's no freeing or moving or anything to do at this point. So now we have the last use in the fee of v3 and v5. So we can get rid of those. And we need to allocate v6, but v6 was already allocated because we did it with all of the fee. So again, saying that if it was live at the same time, if there was already something in there, then we'd be broken. So we move v6 into the active. So now we're trying to allocate this add at the bottom. We've got the last use of v0 and v6, so we can go and free those up. And now we need to allocate v7, and we've got R1 just sitting there with nothing in it. And at this point, we've allocated every instruction, and so job done. And what I assert is that this is the same as linear scan, but with no intervals. And the only thing it's doing is doing live at the same time tests and using this future active set.
How does your allocation quality compare with
graph coloring?
With linear scan, it's identical.
Graph coloring.
Yeah, identical linear scan, like graph coloring. For a large purpose. You've done all this, right?
Sorry?
You've done all this work, right?
Yes. So graph coloring and linear scan, there's been work showing that on PowerPC linear scan can outperform graph coloring and this, that, and that. And what it really comes down to is like the tweak and optimizations and the heuristics that you can bake into your allocator. So that little Rex prefix trick that we did on the client compiler, if you were doing accessor methods, then you could potentially get better register allocation out of C1 and C2 just because it was doing a dumb heuristic on the size of the instruction.
You can do that back in C2 as well.
But who cares that much? But my feeling is that between graph coloring and linear scan, there's been a lot of work, and LLVM is still, it's doing its greedy register allocator, but the greedy register allocator is essentially linear scan. What they're doing is they're pre-allocating certain instructions for certain interesting cases, and then they're doing linear scan. And so what they do by doing these pre-allocations, or putting intervals into certain registers at a certain point, it's exactly the same as just putting an instruction into the future active set. I think the algorithm is as good as linear scan, as good as greedy, and so on. Do I need to go and implement every register allocator and bake them all off against each other, and then implement every heuristic that I can think of for every outer scan?
That's what I got told to go do when I was trying to get my paper published.
Right, and in 10 years, I would be able to go and say, I have implemented, and it would not fit into a research paper. And by the time I'd done it, all of the computer architectures I was targeting would all be obsolete, and so on and so on and so on. And people would go like, what the hell were you doing? And this is because the conference people don't want to accept these papers unless it's it's a cast iron case, or unless they're accepting a paper for their friend. And so there's kind of two things that go on.
All right, let's not get bitter about papers. We've both been down this path. So I guess think what you've done here is very cool.
Yeah, and I'm just trying to understand not so much about whether it's precisely better, but whether it's something that I should consider implementing when sometime in the next 2 months I need to implement a register allocator.
So let me get to the next slide. So this is why you should. And this slide is unreadable. And Cliff asked me to add colors, and I added color to the text, and I didn't add it to the graph.
No, I had to ask to the graph. Fine.
And so what I wanted to say in this graph was, well, we're trying to say that you don't care about overlapping intervals or edges in graph coloring, but can we go and measure that? And the thing that we want to know is live at the same time. So we can look at, when we compile a method, how many times did we call live at the same time for compiling that method? Yeah, how many live at the same time tests were there? And it's the y-axis is logarithmic, so it's the y-axis is telling you how many times we called live at the same time, and the x-axis is telling you like a cumulative number of methods. So the first line that should be a different color on, isn't it? It's kind of like line dot line dot. The one on the left that's starting around about 81.5 or so. This is for any live at the same time test. So either between blocks or within the same block. Okay. And so for 80%, everything that's to the left of that, 80% of methods, we never did even one live at the same time test. Okay, so if you're compiling an access method, you're putting, you're generating a get field, it's going into a register, you put it in that register, it's used by a return, job done. Okay, I never needed to ask, the value I'm putting into a register, is it live at the same time as anything else? It never happened. And so for compiling the entirety of Android, which I would say was a fairly large, data set, for 80% of methods, you never even ask the question once.
You need more inlining.
One, Android ProGuards, so it does inline at the bytecode level and so on. So that's a fair comment. With inlining, you'd expect this number to be smaller, but yeah. The other two lines are breaking apart.
Isn't it also the case that for an accessor or something, the graph that you would build is basically one edge or something? It's pretty trivial.
Right.
Yeah.
But it's probably twice the size of your. It was probably doubling the amount of memory you're using because it's probably a similar size to your IR.
Yeah.
Okay.
I would claim if it was an accessor, you should have been inlined, and this isn't a question.
Yeah.
So instead, after inlining, you've got some bunch of big methods. Now the question's exciting, and I don't know what your rules are for inlining in your ahead of time compiler.
This isn't for the ahead of time compiler for art. This is actually an internal bytecode optimizing tool.
Okay. Okay.
Okay. So so like Google Maps, everything else like that. So all of this like internal like core bits of Android are all compiled using this. So we've got the how many times alive at the same time asked, and that's that left-hand curve that when we get up to 100% of methods, we've had some outliers, and so we've had many calls to live at the same time. And I've broken apart when it's done for different blocks or when it's done within the same block. So when am I asking, is this value in here? And there's another block. Are they live at the same time? When it's between two different basic blocks, you can basically say, well, is this guy live into that basic block? And if he's not live into it, then there's no way they can be live at the same time if that guy's not live out. And all of the rules are written down in the paper. There's a bunch of them, but it's not egregious. So the other interesting thing on this graph is that it goes up very high on the right. Okay, so what that's saying is we had to do a whole bunch of live at the same time tests, thousands of them, in like this 1% of cases, or it's a fraction of a percent of cases. So what's going on there? And what it is because we're generating bytecode, the array operations need you to put the array index into a register. There's no kind of like array access with array offset in it. So then you have this question about well, if I'm compiling a huge class initializer with tons of arrays in it, I can potentially share the constants between all of those arrays and avoid materializing the constants for the array accesses. And why we're doing all these live at the same time tests is we've got these very long expanded liveness intervals because we've got the sharing of the constants, and we're trying to fit things into the nicest hole and to kind of like make it of the most use for the future. Now, this class initializer problem and not being able to put constants into array offsets is a very particular problem that you get into when you're generating bytecode. And you can have a rule like just rematerialize constants immediately before their use. Okay, we didn't do that because we were trying to do better. And this was such an outlier that it didn't really hurt us in overall compilation time to be playing these very aggressive games in trying to fit constants into registers. But in a regular JIT compiler, I don't think you'd ever hit this.
Right. This is a example that certainly an x86 or any RISC chip would not. This particular case would not hit. You just hold offset. And
that's what accounts for this big spike over on the right.
I'd love to see the same set of numbers on a compiled x86 corpus with some inlining.
I need to stop the world, freeze the world for a bit, go and implement that, and so on and so on and so on, and then get back to my day job and pay the mortgage and all of these things that I need to do in life.
Yeah.
I don't disagree with you. I really hope that somebody. Well, I know some people. So I did all of this. Do I mention that? Yeah. I'll talk about the fun things in a bit.
I have another comment here. I think your live at the same time test is basically computing. It's like a sleazy, cheesy approximation to interference graph without building it. You have an 80% conservative approximation or 90% conservative approximation to an interference graph at no cost.
Yep. That's what it is. And you could equally go, oh, I've realized I'm in one of these cases where I need live at the same time. At that moment, compute the interference graph, and then use and so on. It's not what I've implemented. I implemented this.
You could do an interference graph within a basic block almost. Looks like your approximation says at block boundaries I can cut you off pretty quick.
Yeah.
Interesting.
It.
Fine.
So
I
started doing all of this work And I went to every register allocation person I could find. And, I went, everywhere inside of my company and so on and so on. And nobody had done this. And having explained it, it now feels obvious. Yeah. That you can just basically do a lazy linear scan, but nobody's ever done it. And that's why I thought it was worth sticking into a paper and wasting a whole bunch of my time doing it, because I would have appreciated coming across this.
I don't know how you publish these things without going through the official route such that they can get discovered. It's a findability problem. Hey, I got a cool idea. I want to write it up on a blog. Maybe Google finds you. If somebody else is hunting for it, maybe they don't.
So I did. I put my paper on the Wikipedia page about register allocation.
Oh, there you go.
Yeah.
Oh, I could do that.
When I put the paper on archive, it was the most read, most cited paper on Reddit compilers.
Nice. Okay. Excellent.
And nobody, it could be I'm full of shit. Nobody to this point has and the work's been out for going on for 5 years.
I don't recall seeing this, and I kind of consider myself a reasonably expert register allocator writer.
I've shown it to Chris Latner. I've shown it to Vivek Sarkar. I've shown it to the people that you'd expect would know as well.
Yeah, right. Fine.
To get it approved to come out of Google, you have to send your publications, and they have to say whether they want you to put it out the door or not. And I was like, oh God, they're going to say no. I've done all this work writing a paper, and they're going to turn around and say no to me. And I had to get it signed off by Sanjay Gemawat. And Sanjay and the ML guy, he's everywhere. But anyway, those guys all cut their teeth on Java and doing VM optimizations and so on, and they considered it worth getting out the door. So program committees, I hopefully they're kicking themselves and saying we missed this one, but they probably won't. But okay, some fun things. You saw that I kept doing this last use test because that's the thing which tells us we can unfree the register. Now, a nice property of SSA form is if we do everything post order from the end to the beginning, then we get to the definition after we've reached all of the uses. So if we allocate it at use rather than at definition, then our last use test just becomes, have I reached the definition? And this is a nice hack. Somebody said that somebody's told me backward allocation sounds interesting, and I was like, does it? And I spent a bunch of time figuring it out, and it was like, yes, it does.
I've done it both ways before. Yeah.
The V8 mid-tier compiler had access to this paper, was inspired about it, did backward register allocation. They don't do the live at the same time tests and so on. They just spill everything. It's like, it could be, let's just have a stack slot for this thing, and we'll just have lots of stack slots.
When you say mid-tier, V8 mid-tier, you mean maglev?
Yeah, I think that's what they're calling it. We looked at doing, we were like, when we started doing this work, a lot of people were going like, oh, you should do PBQP because it's optimal.
No.
Well, it's optimal in the same way instruction selection is optimal. It's like, given this cost model we have, so on and so forth. And I could come up with pathologies to it. Something that somebody told me, and I thought was a really interesting insight, is so static single information is an interesting thing. It's where in SSA, every definition dominates its uses, and in SSI, every use post dominates its definition. And how does that work? You have a branch, you end up having to create little extra, I think they use pi a lot, but they have a pseudo instruction on entry so that the definition post dominates the use. But if you go into SSA plus SSI, then these ranges that you have look very much like kind of like live ranges, and you kind of maximally split the IR, and then that means that you don't need to look at live range splitting. You only have to look at live range coalescing, which is it's an interesting insight. But it didn't motivate me to go and implement SSI because it's already a pain in the ass to maintain SSA. Maintaining SSI and SSA, my hackability score has gone down.
Yeah. The other thing in my head was there's no frequency information in all of those choices, and you want to make sure that your hot shit gets allocated a register without any spilling. And outside of the, in the low frequency regions outside of the loop, you kind of care less. And this kind of splitting thing didn't split in the right places. You wanted to split around the loops so that the cold stuff spills and the hot stuff all got registers.
Yeah, there's lots of, the loop closed SSA form so that you've got a pheno, which is like, immediately after the loop to kind of like nicely coalesce things together. There's lots of things. It's given LLVM is so SSA, it's bizarre to me that their register allocator isn't on SSA form, and it's also very heavily kind of like linear scan in like the abstractions that they push towards. The PBQP stuff just completely replaces the whole thing. Thank you for letting me talk too much. I'm hoping the stuff was fun. I recapped the 4 things I mentioned: read barriers without an extra read, software transactional memory for doing AOT class initializers, a concurrent non-moving sticky generational garbage collector, and then the last one was
more jargon words than what I recall most garbage collection papers have. Yeah. Sorry.
Yeah. And I think I've already mentioned the stuff. And then I was talking a lot at the beginning about like me dying, so I had a little animated GIF of a tombstone. I tried to AI generate one with a fluent thing on it, but failed. I need more time playing around with AI image generation and so on. So you want me to go back and do the right-hand side first, or?
Oh, that would be nice. If you can, hack it somehow as you go, or talk it through the hacks, it'd be a fun thing. Like go back to the first block and just be quick on the first block because that's not changing.
Yeah. So we're gonna go to. So we're not doing this side. And if I edit the slides, then you say
don't be so smug about it either. So.
Say again, Kirk.
And don't be so smug about it this time.
I know I'm annoyingly smug. I was talking to I catch the Google bus too, and I was talking to the Google bus driver yesterday because I like Google bus drivers are fun, and I was saying that the things that my siblings did to me. So when I got my PhD, my brother goes, "Oh, you're Dr. Ian now. That means I can call you Drain," and so.
That's good. I like that one.
Right. It's like, why isn't everybody calling me Drain? It's yeah.
Well, I was trying to figure out why your handle, where did I see that your email or your Discord handle had 3 I's at Rogers? Ian Roger.
Yeah, I was trying to come up with. So I used to be on Telnet Talkers, and like back then I got a handle of Captain 5050. And because I created a GitHub account like at the dawn of time, that's my GitHub thing, and I don't like it now, but it's stuck. Yeah, when you were a member of staff at Manchester, you put your first name initial before your surname, so it was a measure of status. But Twitter wouldn't let me have iRogers, so I needed a few extra iRogers in there, eyes in there. So should we do this right hand side thing?
Yeah.
Let me. Is that still? Is sharing it as that? Okay. How about I like copy and paste it as new slides so that then I can like either delete it or we can keep it or whatever.
Sure.
Okay,
I was going
so
to suggest, why don't you just copy the slide and wipe it out and restart?
Yeah, just copy like that. Yeah, right. Copy the first slide or somewhere in the first slide, and then start pasting new, or just edit the one throughout
Right.
the live video. Just take
Yeah,
one
okay.
copy and edit it.
Yeah.
So you can watch me recreate my process. So we're going to allocate the right hand side first. Boom, 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 boom. So that guy shouldn't be so highlighted.
You don't have to worry about all the edge arrows things. We're all good here.
Yeah, don't worry about highlighting. Just get to the good stuff.
Good stuff. Okay, we've got the live outs are V0, V1. The live ins are V0, V1. Are the same. Okay, so we don't need to worry about this stuff down here. Okay, so because they're exactly the same, there's no work to do to kind of like free a register or move something which is active into to future active. Okay. So then I still want to call out. So but I just don't want that text in that. Let me edit the text. So now we're going to allocate V1. Yeah. Oh, sorry, V4.
V4, yeah.
Yeah. So we're gonna allocate V4. Sorry.
Yeah, allocate V4, and it's the last use
No,
of
no.
V1.
Before you allocate, you're always free.
Yeah.
So we've got the last use of V1.
A question: Do you not look at the fact that V1 is the last use and V4 is, so therefore you do a kind of move biasing thing and just say use the same register? You're actually explicitly freeing before allocating.
The move biasing thing that's done by C1 is basically you just remember the last freed register, and then when you allocate into the last freed register, and then by virtue of that you end up with the biasing. So I've only ever done that trick.
But it works here. So you don't, if you do nothing here, you get the right answer. You free V1, you reuse, I'm sorry, you free R2, you reuse R2, you're done.
Yeah,
Okay,
in this simple example.
Right.
Yeah. So we freed V1, so now we need to allocate V4. Okay. Okay, so we're on the second slide. So we've just done the allocation of V4, and hopefully we can all agree that V4 should go into R2 because R1 was already busy with V0 in it. And now we've got the last use of V4.
Put the register assignment on the our V4 gets from V1.
V4 is in R2.
Yeah.
Yep, we good now?
Yep.
Okay, so we've got the last use of V4.
Which means you free it.
Which means we free it.
V move.
And then we need to allocate V5, which is a phi move. So now we're doing the allocation of V5. Obviously, it's going to go into R2 because it's the only thing. And we need to think about, is there anything that's going to be future active in R2 that's going to interfere with V5? And there's nothing possibly future active in R2, so we can put V5, V3, and V6 all into R2. Okay, so let's do the next slide.
So I have a question regarding that, what you just said. If you have multiple selects out of a block, then can you only do this trick where you're pre-allocating on the last one? No, you can do it on all of them, right?
Yeah.
You do all of them, yeah.
And like a select, there would never be anything after the select, would there? I thought, oh, I was always putting all my selects at the end of the block.
You're what he calls fee move.
Fee, yeah.
Yeah, you're calling it a select. Yeah, they go at the end of the block, but they
Yeah.
are simultaneously applied at the end of the block.
Yeah.
Not ordered; they're simultaneous.
So the idea that saying, oh, there's nothing after it, maybe that would be something that you'd look at for like the V4 assignment if that had survived out of the block. But for a V assignment, that's not really a relevant consideration.
Yeah, I think
Go hack the fee moves for V3 and V6 too, to go add the register.
Oh yeah, okay, yep. So they're in R2. Let's make that box wider.
Yeah.
Okay, so we've dealt with the fee move on the right hand block, and so now we need to go back and handle the left hand block.
Yeah.
Yep. Okay, and it's easier just to copy this guy than try and recreate it. So we just did the fee move there.
You're going to get a different allocation, I think.
Yeah, no, I'm just trying to work out what I've done with my slide deck. Let's copy that guy because that's the one with the.
Yeah, let's take that guy.
Yep, this guy. Okay, so now we're doing this side. Hold on. So the live outs were V0, V5, and it's different from the live ends, which are V0. Is V5 used in the future? Yes, it's used in this block at the bottom. If it's used in the future, then we want to put it in future active. Otherwise, we want to go in free R2 V5.
But it is used, so you're just going to move it into the future.
Yeah, so copy paste. So now let's get rid of this guy. And V5 is going to be used in the future. So it's over here. Okay, and then we want to allocate V2. I'm sorry that watching me write slides is painful.
No, we expect it for the live demo.
Yeah. So we 3 is a constant, so there's nothing to free. So we need to allocate V2.
Yeah, on the left. Yeah, right.
Right. And so when we do this allocation, R1 has got something active in it, so let's not even bother. R2, we need to do an is live at the same time test for V2 against V3, V5, and V6. Yeah.
Yeah.
Mm-hmm.
And so so it's not live at the same time because we're going to immediately free it. So this is the.
It's not live at the same time because the next fee move is using V3, V5, V6, not V2.
Yep.
Okay.
So we've got the last use of V2, and so free R2. So this guy becomes free. And then
you didn't tag the constant instruction with the register.
You're right. Let me go and stick that in. So you are in R2. So now we're going to allocate our V3, but V3 was already allocated. So what that means is we just need to move it from the future active to the active.
Just a question from my understanding.
Mm-hmm.
When you're doing a live at the same time test, you are looking at the whatever is in the future active column for for the register you're interested in?
Yeah, you first
Right.
look at the active, and that's just basically is it null or not.
Yes, is it
and
empty?
then yeah, and then you have the future active, which an easy way is to just have an array of instructions, and then you just iterate through it, and then you do the is live at the same time test on each
Okay.
instruction in turn.
So then the way that you select a register, assume it, first of all, valid registers and available, and then you just find the one with the least future active.
It has to have no future active or you're going to be spilling. This example doesn't spill.
Well,
Right,
I would
so-
think that you would minimize your future active tests by once you've got, say you've got, a normal number of registers, and so you've got a few to choose from. So you've got, R2, R3, R4 are all not active, but they all have, they have 2, 3, and 4 things coincidentally in their future active. So you'd want to choose the one with the least number of future active, right? To check that one.
There's absolutely nothing stopping you from doing that. It's kind of a heuristic to make the allocation time fast. I didn't do that, so but there's nothing. I was literally I had a whole bunch of other dumb heuristics, and I'm doing it on a bytecode, and the bytecode has an unlimited number of registers, but only the bottom 16 registers could do everything. Then the bottom 255 registers could do some things, and then you had like up to 64K of other registers, and there are ways there are similarities with this, and kind of like the high numbered registers are kind of like spill slots and things like this. There's ways. Linear scan has the same problem basically, and so you can tackle it in the same ways. The paper doesn't do it. It would be interesting to go and implement all of this for x86. It would be interesting to compare it with me re-implementing a graph coloring register allocator, so on and so on and so on and so on, but lack of time. But I agree with you. To be honest, there were so seldom things in future active that it wasn't dominating performance, and I was trying to come up with more dumb heuristics. So one of the dumb heuristics would be things like, oh, you're doing a bunch of things with the same string buffer. So we had a thing which would remove the builder pattern from string builders. So with a string builder, you pass into this pointer and then it returns the this pointer. Yeah. Mm-hmm. Well, why don't we just keep the this pointer in a register? And then because of the way that they require that the registers in Dalvik are passed as a range, so they've got to be consecutive. And so if you want to reduce the code size, you've got to minimize the moves. And so you're trying to align the arguments to the function calls. And so there was a lot of games and heuristics and playing around with those kind of things, trying to minimize the register allocation time was practically zero anyway. It was the paper breaks it down, but the register allocation time was about a third of the time was computing the liveness, and then 2/3 of the time was actually doing the register allocation. And what it would do is, if it thought that the register allocation wasn't as good as it could do, it would just restart it again. And so the paper breaks down like how many times it would just keep restarting the register allocation to try and aggressively apply all of the heuristics it's got. And I think there's room to do better with that. But the first thing I would do is start doing the register allocation backwards, get rid of the last use tests, and things like that. But I mean, the only thing that's left to allocate now is, we have to free up the states from the live ins match again. So there's nothing there. We've got the last use of V3 and V5, so we free those up. So shall I write that down?
Yeah, whatever. I think we're.
I think it's the same as of here, right? So
yeah, I think we're done.
Yeah,
I got what I needed. I wanted to see if you were going to run out of registers in the reverse side and had to deal with picking a new register or spilling or anything, but you're not, because the example is too small, which is fine.
It was Ross McIlroy's example that I've stolen, because
Oh yeah, you gotta
It's
fit on.
difficult to come up with a reasonable example.
Yeah, exactly. I do it all the time where I've got, got to fit it on a slide. You got to make it readable, and we're at 2 hours, so now I am going to start calling quits here. So in fact, why don't we stop with this and see if there's any last questions or change of topic or anything else anyone wants to cover, and then we'll look for winding it down here in a few minutes.
I have a few questions about the performance of the implementation. So I remember reading this paper. I saw it on the subreddit actually, and I did see a graph there. I think it basically said that liveness and pre-allocation are like two of the chunky phases that take up a lot of time. And could you maybe go a bit more into detail, like what exactly is taking up time there, or like how could you improve things, and maybe yeah, I don't know, like yeah, I don't know, like also are there some like opportunity costs? Maybe like I feel like some ways of doing register allocation are more like amenable to choosing data structures that are easier to iterate over, or that are like have better cache locality, or can be used like SIMD optimized or something. Like, any thoughts there?
Yeah, so I in the compiler that I did, it wasn't like data oriented at all. And so like in the hotspot C2 implementation, it doesn't use instruction pointers, it's using offsets into tables and things like that. And I think there's great opportunity to make things more compact, use better instructions, and so on. That was just a lack of time to optimize and to push on those things. The thing that I was really interested in was getting the size of Dalvik code down so that we could ship smaller binaries to people. So you mentioned like the pre-allocation time taking a bunch of time. What that was trying to do is it was trying to play all of these games. Like if I align this invoke statement this way and invoke this other invoke statement this other way, then what kind of register sharing opportunities does that reveal so that I don't need to move things around? And so it was just lots and lots of dumb kind of like heuristics. The effect of pre-allocation is to put more and more things into the future active set because you've not started any allocation yet. You're going to allocate, and you've already said these things must go in these registers because it's good for performance. Even in that situation, like the numbers which they're showing the 80% of the slide that I've got up there, that's with the pre-allocation. And so we're still doing 80% of methods with no calls to isLive at the same time.
Really amazing.
I see. Thanks.
And I think there are lots and lots of heuristics and so on. So Google has rolled out a machine learning register allocator, and I ask people, well, what are the heuristics? What's it found out? What's the cool thing? And what they go is peanut butter effects. Oh, it's peanut buttered everywhere. You can't blame a particular thing. Now, somebody day job working on profilers, that disappoints me because I want to be able to find your chunks of peanut butter. But what I suspect might be happening in that case is that maybe it's stack alignment. Maybe the register allocator is learning to put 4 things onto the stack so that it better aligns the stack. And it's getting caching effects and things like this. There's who's the guy on the East Coast? University of Amherst.
At UMass, doing register allocation?
No, doing he did a paper where he managed to get a
Emery Burger's stabilizer.
Yeah,
yeah.
And Moss.
Emery Burger.
Emery Burger.
So,
okay.
Yeah. So there's all of Emery's work where it's like he managed to get like O3 code to perform at the same speed as O0. Okay, by just changing things like stack alignment and code layout and things that shouldn't matter, but actually microarchitecturally they do
Matter a lot.
A lot. Memory alignment.
Right. And so that's, it's still an open to try and figure out from these like machine learning register allocators and so on, what are the actual heuristics that are kicking in every once in a while, and what can we do to benefit from them? What are they? I'd love to see it.
Are you saying that there are some machine learning register allocators that are doing better than heuristic ones right now?
Yeah. Oh, I'm so bad with names.
What you were just saying is
Marcia Trofan, I think, is the guy who's been doing it at Google. I can put that into the chat.
yeah, okay. And then maybe somebody copy it into the docs. We usually put these things in the Google Docs so that it can be found later.
Yes, sorry.
I don't know the name.
Yeah, so it's Marcia Trofan. He's done work in that area. One of my things with the memory renaming stuff is like, well, if the hardware can allocate things into registers for us, why do we need register allocators at all? So
because hardware is always finite and you just ran out, so you're gonna anyhow end up doing something.
It's not about register allocation at that point. It's about resource management.
Register allocation is a version of resource management. Yeah.
Well, yeah. I mean, if you had infinite registers, then
right,
you wouldn't have to worry about management.
Right, that's what he was saying. Hey, the hardware will just do it because it has infinite. No, hardware never has infinite.
No.
So,
I was
management.
I was always interested in register windows and what it means for, like, because like what we spills and fills, it makes sense to do them with the memory coherent stuff for C, but for managed languages, we could be spilling and filling. We don't really care how the stores and loads get reordered as long as they respect each other. But other than register
work on register windows, I did Spark, Itanium, and Azul as 3 different versions of register windows.
Was Vega register windows as well?
Yeah, totally. It was variable. Didn't have to do chunks of 4 like Spark, but yeah.
We did an alpha inspired instruction set where it had a token that was passing around the bus, and the token would tell you that you had like a hyperthread context which was available, and so it could do hardware. You had a call instruction that was either call a function or it would fork.
All right. Now we're definitely getting into random, weird, fun stuff, but also past our time here. All right.
Oh, this Emery Burger thing is quite interesting. I've actually done this. So you have just separate processes that just take up random amounts of memory so that you can just realign executables in memory with it.
Yeah.
And just look at performance differences just because of memory alignments.
Yep. All right. I'm going to call it. This is a lot of good stuff we can talk about next time, including stabilizer or any number of register allocation heuristics. There's no end to them.
Stabilizer looks like it's more like I'm going to randomly move things around on you.
He was getting statistically measurable small effects by causing many other effects to get random. So you defeat randomness with statistics. And the issue is, the old paper, how to get wrong numbers while not doing anything wrong or whatever. It was all about, hey, we accidentally fiddled with the cache line because I changed the name from Emery Burger to my student's name. And the name changed the env size, changed the stack offset that the hot loop ran at. The hot loop now split across a TLB boundary and run 50% slower or something stupid. And all we did was change the person's name. It's like, oh crap! How do you manage for that kind of difference? And so Emery said, we can manage for this randomness, statistics, and there it is. That's stabilizer. And it's a good paper. It's great stuff. It's how you deal with, like, why is it faster or slower? I did many years. I saw these papers and I did this work myself where I did some stupid hack and hey, it got 5% faster, but I got, I fiddled with numbers until I got 5% out. It turns out that statistically speaking, I was getting noise. and I did somebody else's thing and they said this and it was noise for me
Yeah.
and it was all noise. And if everyone had done 5% of every paper that said you get 5%, compilers would make code run 1,000 times faster. No, all them 5% were all cherry picked too much, this and that, not repeatable. So I'm very much like Emery's work on this, but it's time. I actually have to go soon because Lisa tweaked her knee. There's a story. She read a thing that said, hey, when you get past a certain age, you can't skip anymore. And I was like, I can skip. So I went skipping around the living room. And the cat was having fun and chasing after me and whatever. And Lisa said, I can skip too. And we went skipping around the living room and then she tweaked her knee. And now she's on crutches and got an x-ray and we got to go back for an MRI
and you're still skipping around the living room.
I'm still skipping, but I have to actually go drive her to the MRI because she can't drive right now.
Because of her knee.
Because of her knee, yeah.
So I guess
So it
it's
was 50% right.
Yeah. All right. I'm not even going to try to knock on wood here to keep my knee from tweaking. I'm saying, nope, I'm good. Damn it.
If anybody's got questions about any of my stuff, then feel free to reach out to me.
Yeah, I mean, we have your number.
It was extremely interesting. Thank you for the presentation.
Yes, thank you very much.
It was amazing.
Agreed. Yeah.
Really nice.
All right. Bye-bye.
And, and not too smug this time. That was really nice.
Sorry, thank you.